Hello, guys, and welcome to the problem solving sessions on system design. In this sessions, we'll be solving HLDs and we'll be having deep dives on certain aspects of HLDs. For today, we will be having YouTube system design. Now, you'll ask me where are these HLD interviews and for what candidates they are being conducted. So, usually for the internship level or for the entry software engineering levels, the HLD interviews are there. So, let's start with the YouTube system design. Usually in the HLD interviews, they take up the system that you are aware of, like for example, YouTube, Uber, or Ticketmaster, or something like that. But if you are not aware of a certain system, like let's say ad click aggregator, then you should communicate with your interviewer effectively and he must make you understand what is the system about. And that's when you can actually jump into the problem. As you know, you might be probably watching me on YouTube only. So YouTube is a video sharing platform. We will be moving in a very structured way. In the structured way, I mean, we'll be first gathering the requirements, then the core entities, then we'll do the capacity planning and estimations kind of a thing, and then we'll jump onto the HLD and then deep dives on the certain aspects of HLD. And to by deep dive I mean, we'll identify single point of failures and we'll assume certain math, and then we'll decide whether to scale up a feature or a service or not. We'll also decide whether we are going to move with a monolithic or an microservice architecture. So that's where the problems is kind of there. For YouTube, managed by Google, we have multiple teams, and each team has many members. So I think we can have microservice architecture as well, as we can focus on independent features. So let's start by gathering the functional requirements. So now you'll ask me, what are functional requirements? Functional requirements are is kind of like a contract between you and your interviewer, like on what features your solution will be focusing on. Like for example, YouTube has been operating since like 2000s, and they had like 25 years now to scale the system, and you have like 45 minutes of your interview. You cannot design entire YouTube in just 45 minutes, right? So it's a contract between you and your interviewer that hey, I will be focusing on these features only, and will let the other features be kept aside. For now, for today, our problem will be majorly focusing on the uploads and watch video kind of features. As YouTube is majorly a video sharing platform, there are creators, there are viewers. Creators upload their video on YouTube, viewers watch that video. So we'll be focusing on these two features. So let us right now write down the functional requirements. Sorry. So as I mentioned, functional requirements is users can upload video and viewers can watch any video. Okay. So yeah. Okay. These are the two major functional requirements. Other than these, we have like the authentication kind of a system, YouTube Live, YouTube comments, YouTube likes. Then YouTube Premium is also as well, but we cannot design entire these features in just 45 minutes. Let's keep our functional requirements right now this much only, and if we have time, then we'll add one more functional requirement and then implement in our system design. Okay, so now that we have done functional requirements, let's now write about the non-functional requirements. By non-functional requirements, what do I mean? Right? Non-functional requirements are the features of your or the qualities of your system. Qualities in the sense, how much scalable do you want? Do you want to focus more on consistency or availability? The major first point which comes to my mind while discussing the non-functional requirements is about the cap theorem. Now that you are watching me solving system design problems, I expect you to have a good knowledge about the core subjects such as C and DBMS and OS. Now, we'll first discuss about cap theorem. Now, cap theorem in the sense is like you can have the two of the things at a time and not the three. Now, what things? Consistency, availability, and the partition tolerance. Now, partition tolerance is taken as mistaken for granted. So it's a trade-off between the availability and the consistency. For YouTube, YouTube is like a worldwide platform. We have viewers and creators from the US in from the India as well, and we have our YouTube in function for like 24/7, 365 days. Also, the creators might be uploading videos 24/7, 365 days worldwide, and viewers are watching it worldwide for that particular time. I think we must leverage on the availability instead of focusing on consistency. So I think I am locking availability over consistency. You can take help of your interviewer at any point, and that is encouraged as well in interviews. It's not a one-way conversation. Like I know I'm like teaching right now, so it's a one-way conversation. But in interview, it should be a discussion, not a teaching kind of a thing. Okay. Also, uh, non-functional requirements. We also discuss about latency. Now, let's say I'm a user and I do want to watch a video created by Mr. Beast in United States of America. Will I wait for 5 minutes just to watch a minute, just to watch a 1 minute long video? No, right? It would be a pretty bad user experience. So I think low latency should also be feature kind of a thing for our system. Latency. Okay, so we have availability over consistency, then we have low latency. Also, a creator should be rest assured that when he clicks on the button upload, his video is uploaded for sure. So our system should be reliable. And a viewer, when he clicks on a video to watch, he must be assured that in next few seconds he would be watching the video. Okay. So our system should be reliable. Okay, okay. I think things are pretty clear till here. Like we have non-functional requirements, we have functional requirements. I do not encourage to jump on to doing capacity estimations and planning at the very beginning. If we need to take up a decision, then we should jump onto the math. It would be a waste of time if we just do it in a sake of uh, in sake that to take up a decision whether it would be a distributed system or just a monolithic architecture. It's quite obvious that YouTube would be a distributed system. As we have mentioned, like we have 2.5 billion daily active users interacting with the YouTube platform. So just for your understanding, I'll be doing the capacity estimations and planning right now, but usually you shouldn't do it at the very beginning of the interview. And if you are an intern kind of a thing, usually it's not expected that you should be aware of the data of daily active users and stuff. You can ask your interviewer as well. So I'm just estimations. I'm also, estimations in kind of a sense that you are doing a calculated guess and not an actual kind of actual data. So roughly, I'll take an assumption that we have like 2.5 billion DAO. It's called DAO. I mean the daily active users. Let's unbold it. Okay. Now, let's say I'm a kind of a person who is brain rot and who is watching 10 videos a day. And in the worst case, there are 2.5 billion people who are watching at least 10 videos per day on an average. Okay, so that means we have to serve 25 billion videos each day. That comes out to be 1 million videos per second worldwide. Okay, now we have like one, sorry, I think I'm kind of wrong here. It's like 300K. I have my notes as well to just help me out. Okay, 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 okay. So let's say we have like 300K videos per second being served worldwide to serve it. Okay, okay, okay. Now that we have it, in general terms, the number of people watching the videos are greater than the number of people uploading kind of people. Like the creators are less in number than the viewers. So let's assume that for every creator we have 100 viewers. So this is the ratio, creator to the viewer ratio. Now why do I write it? To get the sense that our databases storing the videos must be read efficient or write efficient. Okay. So let's say we have 300K videos divided by 100 per second. So we have 3000 videos being uploaded per second. Uploading. So this much amount of data. Okay, so we now need to get on to the details of how much data we need to process each second. Let's assume each video kind of being like 1 GB of each video. 1 GB per video, I will say. So we have kind of a thing like 300 GB of data incoming into our platform per second. That boils down to 3 terabytes of data per second. Okay. So we need both read efficient and write efficient databases. We'll just keep these points in mind and we'll take up this particular estimation while deciding what kind of and what type of database do we need. Okay. So I think capacity estimations kind of a thing is pretty done over here. Now we'll discuss what kind of entities will be taking part in our system. Entities by in the sense like users are there, creators are there. Creators are creating videos on the YouTube platform and viewers are watching those videos on the YouTube platform, right? So the core entities are pretty clear. Uh, Core entities, as I mentioned, would be users, creators, videos that are being uploaded on the video, I think, I mean the YouTube platform. Apart from this, we need to also store those videos, right? So we need databases. That's pretty obvious. And we need our servers as well to process each and to serve each kind of APIs that are being hit. Okay, just a moment. Yeah. Taking these 4 points in mind, now we'll discuss what kind of APIs do we actually need to make our system work. Now, usually, when we discuss about the functional requirements, there is like one-to-one mapping. Each functional requirement maps to one API. Usually, that's the thing. In the worst case, like in case of like Twitter or something like that, one functional requirement might give rise to multiple API points, like internal APIs and an API exposed to the clients. For now, in case of YouTube, that's not the case. I think there is a one-to-one mapping. So users can upload video. Now, what is meant by upload? Upload is kind of a thing like you are creating data. Now, in case of creating data, that would be a post request kind of a thing. If you have done development kind of a thing like in Stack or something like that, you might be aware of post, get, patch, delete, update requests. Not getting much into details of it. Okay. Now, post request, we also have to give the body of each API, like each post request API. Okay. Uh, in body, okay. So this API would be generally hit by the creators, the one who is uploading the video, uploading their unique video. Now he must pass the video data. I think by video data is like the actual MP4 file or the .h265 file. Okay. Apart from that video, he needs to decide the thumbnail of it, then the caption, title, description, then boolean like the boolean variable he needs to set, like whether it's for the kids or not for the kids, like restricted for the below 18 years age and stuff. So that's a pretty structured data that YouTube asks each and every time while a creator is uploading a video. So instead of mentioning each and every aspect of that, I'll just simply mention video metadata. Keep in mind, I said it's a structured data. YouTube metadata, like YouTube video metadata, is kind of a structured. And apart from that, let's mention the details of the creators. Uh, in the sense, I'll write like miscellaneous details or the data that we need to pass in the body of each API. Now you'll ask me, you haven't mentioned the data of user, like the data of the creator. I usually don't encourage to pass each and every data in the body, like uh, the user, the authentication token or the session ID should be mentioned in the header file of it. I think the header, what you pass with each body, it has like JWT authentication token or the OAuth or the session ID or the cookie kind of a thing mentioned in the header of each API call and not in the body. So we'll just simply mention session ID or the token in the header of each API. Okay. Okay. So I'll just quickly bold this. Okay. 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 No issues. Now let's get on to the second API point, which is a kind of a GET request. Now GET request in the sense viewer is watching, viewer is wishing to watch a particular video. He clicks on that video and by clicking he indirectly hits an API that, hey, give me the data of this particular video ID. So the get API should obviously have the video ID. So let's mention VID. Now colon something is like it's a replaceable kind of a thing. Like up after this particular slash in the URL, you are replacing this VID with the actual video ID. Now, what kind of response this GET request will give is a kind of a JSON kind of a thing having the chunks of video chunks I will mention. Okay. Um, as well, the post request will have the response of, let's say, if you are a good engineer, then usually it would be a okay kind of a thing, like 200 status code. Okay. So would be the format of the second API, that is GET request. Okay. Now keeping this all 5 points in mind, we'll jump on to the HLD kind of a thing. Okay. Okay. First of all, let's discuss. I think we'll first note down the core entities taking part, like in the actual HLD kind of a thing. Now that we have like clients all over the world, I'll just simply draw the clients in form of a cloud, stating it those are worldwide. Okay, so we have clients worldwide sitting Japan, Australia, India, United States of America. Also, they will be hitting our API gateway. Now that we have like 45 minutes of interview, we can't focus on each and everything. So I'll just quickly have the third party API gateway like AWS API gateway. You can read the documentation on the detailed like API documentation on the AWS website. Okay. Let's have the AWS API gateway. Now, what function does it provide? First of all, the very first is authentication of the viewers and the creators who are hitting these two particular APIs. Authentication, after that, they are doing the routing kind of a thing. Routing in the sense they are doing DNS features. Then, the very important feature is actually the load balancing feature offered by the AWS API gateway. Okay. We have like 2.5 billion active users So we might be having pretty much of a revenue. So we also be having many teams to maintain and to add on features to our services. So we'll be having microservice kind of an architecture. Okay. Now the as you can see that we have like one creator for every 100 viewers. So the uploading kind of a feature should be scaled much more. Sorry, the viewing feature should be scaled much more than the uploading. So we have to get onto a microservice architecture. And that's where we'll be needing a load balancing kind of a thing. So it's great that the AWS API gateways actually offer you load balancing thing. Okay, just a moment. I need to, yeah. Okay. Now these AWS API gateways will redirect the API hit request to our servers. Let's have servers in kind of a round square. Now these are like our YouTube servers. Okay. YouTube servers in the sense they will be handling each and every request. They will be communicating with the databases. I'll just simply, you know, okay. We need a database to store and retrieve the video data that are being uploaded. Okay. So this is a general structure of our system. Obviously, it's not the entire kind of a thing. It's not the complete HLD also. Okay. So this is the raw structure, like a 10,000 feet view of our system. Okay. Uh, let's get into the shoes of creators and let's get into the user flow. I think the creator kind of a flow. He needs to upload a video, right? Does that mean like he needs to upload the his entire video in one go? No. Like for example, he uploads 99% of his video, and what if there is a power cutoff or his Wi-Fi goes down? Will the work of 99% go in vain? Obviously not. You should maintain the progress of 99%. How do we do it? Instead of uploading the entire video at once, we'll be dumping the chunks of the video. Now, what do I mean by chunks? Chunks, like kind of those can be differentiated on the timestamps, like a 10-second video kind of a chunk, or 20-second video kind of a chunk, or 5-second kind of video kind of a chunk. Netflix doesn't do it based on timestamp. Netflix, what it does is it cuts the video in part of scenes, like these scenes of movies or web series or the documentaries. So the user, while watching the video, will watch one scene entirely, seamlessly, and then wait for the next scene. It's not that he will break like abruptly between the scene based on timestamp. Okay. For example, if John Doyer is having a scene of car chase, the car chase scene will be entirely downloaded first and then showed to the user. I mean the viewer, and not like he's about to reach to the car and then he's chasing the car. Not based on the abrupt timestamps. Okay, but that's kind of a Netflix. They have engineered about 17 years now. Okay. So let's get on to the first API that is being served. Okay, just a moment. Okay, okay. We need. Okay. Creator like me will hit a post request, the API one to the AWS API gateway, and he will redirect it to the YouTube server. Okay. Now the YouTube server. Okay, okay, okay. First of all, we need to decide like how to store it, like what database kind of a thing we need to store the videos. Let's get down to what data are we like, what is the data type of the data that we are going to store. Okay, so that's a video. Now, what is a video? Video is kind of a file, an MP4 file or a H265 .h265 video format that is being developed by Apple actually. So those are kind of a file objects. We can store them in case of like a binary large object kind of a thing. Okay. As we mentioned, we need to process 25 billion videos, and there are round about 10 billion videos that are already being uploaded on YouTube. So there is a huge chunk of data that we need to store in our databases. We need it reliable as well because we don't want to lose the videos that are uploaded by our creators. We need it cheap as well, as we have such a database. We don't want our system to use high end databases and run for bankruptcy. Okay, so we need cheap, reliable, scalable, distributed. Why distributed? Because if we store all of the data like in a database located in Japan, and what if tsunami occurs, we'll lose each and every video, right? So we need distributed kind of a thing as well. As well, we need to store it in a kind of a file object, like in a blob kind of a thing. Blob, I mean binary large objects. So keeping these all points in mind, the very first database that comes to my mind is AWS S3. Okay, so we have kind of decided now what kind of database do we want to store the videos. So let's mention our AWS database, AWS S3. It's very cheap, reliable, scalable, distributed kind of a thing. Okay. This is the AWS S3 video data base. Video data database. Kind of a tongue twister. Okay. Also, the metadata that I originally spoke about, like the thumbnail, caption, description, the boolean kind of a thing, then all the stuff. Do we need to actually store it where our actual video data is being stored? No, not at all. It's not required, right? Also, when you open a YouTube video homepage, YouTube homepage, there are lists of it lists like hundreds of videos, right? So does it originally processes each of the 100 videos at very initial point? No. We just need to show the thumbnail, the creator name, the title, and the description, and the number of views on it. Okay. So we'll store them differently, which will help us to retrieve them fast. Also, I mentioned that the YouTube metadata, sorry, the video metadata is kind of a structured thing, and we need a read efficient database. Also, the metadata would be for every video max to max 200 MB. Like in the worst case, like if he uploads the thumbnail in like 4K kind of a thing. In that sense as well, it won't cross 200 megabytes of data. So I think keeping these desired features for a database, the first database that comes to my mind is Amazon DynamoDB or PostgreSQL. So we'll store the metadata differently in either PostgreSQL or DynamoDB. We'll just fix on Postgres. So these YouTube servers will be actually storing the data in the PostgreSQL. Video meta data database, which would be Postgres or Amazon DynamoDB. Okay. And obviously, these are like third party things, the databases like the Amazon DynamoDB and Amazon S3. So we won't be handling the single point of failure stating like we can see like there is only one instance of AWS S3 in our system. So you might say that it's a single point of failure, but that's not the thing, right? It is being handled by the Amazon entirely. We are not going to handle it. They are just going to expose one API to us, right? Okay. So the YouTube servers will be storing the video metadata in the Amazon DynamoDB. Okay. Okay. Now, okay, so we have 25 billion people, sorry, 2.5 billion people hitting our AWS API gateways on the same time where our creators are uploading the video. So they both are hitting the same API gateway. Okay. Now that I am a creator, I need to upload chunk by chunk that I mentioned, right? So do I need the API gateway to process each and every chunk and then pass it to the YouTube server and then pass it to the database? No. It would be a kind of overhead as well to the API gateway. It is already performing functions like authentication, routing, DNS, load balancing, and stuff. So S3 kind of solves it. S3 exposes an S3 URL for each user that is trying to access the database. So what YouTube server can do is whenever a creator will hit the post request, he will request the sorry, it will request the Amazon S3 to expose an unique S3 URL directly to the user, and the S3 will instruct the creator that hey, please kindly dump your video data entirely on this particular URL, and when you are done, I'll take up all the data from the dumped S3 URL. So what the YouTube server will do is request internally. There will be an internal API to the AWS S3 trying to fetch an unique S3 URL. So get S3 URL kind of a thing. And this AWS, now will this S3 URL will be again passing through the API gateway? No need. This will be directly passed to the creator, the S3 URL that I'm talking about, to the client. And then again will be the client will be dumping their entire data on that S3 URL. Okay, just a moment. The shape of this is pretty bad. Okay, I don't need actually. I need both ended. Okay, so we the S3 is passing the S3 URL to the creators, and the creators are uploading or dumping their data on that S3 URL. And when they are done with the uploading of their data, AWS will fetch entire data and store it. Okay, great. Also, the now here it comes. The clients will be exposed only one API, the post kind of a thing. The creators will just click on the upload button. On the first request, they will, you know, give the data like the video metadata, and the YouTube servers will store that metadata into the Postgres or DynamoDB and then hit the AWS S3 with an internal API of get S3 URL. The S3 URL will be indirectly passed to the client, and the system, like the user end system, will then upload it on the S3 URL. So we have only exposed one API at the user end, but we are handling three different APIs internally now. Okay. So it's like post video, video metadata. Okay. So uploading kind of a thing at the end of user is pretty satisfied by our system now. Okay. Uh, Now one thing I do want to mention is there are different kinds of devices and YouTube supports cross platform. Like you are watching me might be on a mobile device or laptop or desktop or TV or iPod, any kind of media, right? Also, if you are sitting in a country like Afghanistan, you might have pretty low bandwidth, or if you are in a village kind of a thing, you might have pretty low bandwidth. I as a creator will be uploading video in 4K kind of a thing, but you might not receive 4K kind of a data. You might be watching me on 144p, 360 or 720 kind of a thing. So I need, so me as a YouTube platform need to process each and every creator's data, the 4K data, and break them down into 144, 360, 720, 1080p for each and every device kind of a thing. Like the laptop device might not require or might not request the video data that is in format of a mobile device. So we need to process that as well, as we are mentioning that our system supports cross platform. So that's also one thing that we should mention in non-functional requirements: cross platform availability or compatibility. Okay. Okay. So right now what is happening is the entire raw data is being stored in AWS S3. So we need a service which will extract the chunks that are being uploaded by the creator. We'll mention this service as um re- what do I call it? Processor, processing service, servers. Okay. Which will retrieve data from the Amazon S3. They will then pass, just to make you visualize what kind of thing that I'm trying to do over here is, let's say we have here like iOS devices, we have like Android devices, and I'm very big fan of Linux as well. Let's select others. Just to partition this entire table. Okay. And here we will store data such as 144p kind of a thing. Here we'll mention data that is supposed to be in 720 kind of a thing. I'm not mentioning each and every kind just to show you what I'm trying to do. Okay. So we need to break down each and every raw data into this particular chart. Chart is not like physically it's not a chart. Just to make you visualize, I've drawn a chart. Like we need iOS 144p, iOS 720p, iOS 1080p, others or like Android in the same sense. So that is what I'm trying to implement in our system now. Okay. It's not a swim lane diagram, it's a transcoded data, I would call it. Transcoded data format. Apple has developed a thing named as .h265. For Windows and for others, it's like .mp4 file that each of this block will contain. So we need to process the raw data into this chart kind of a thing. So these process servers will then communicate with other transcoders. Now I will call them transcoder one. Let's say like transcoder, and then we will having multiple transcoders. Like for example, we have 300k videos being processed at each and every second, and each and every video of 300k will be having, let's say, 100 chunks. So we have 330 million chunks being processed at each second. Okay. Let's say, let's draw one more kind of a thing. Transcoder. Okay. We'll get onto this, like how will one server communicate to these many transcoding services, right? So what is the processing servers doing is retrieving the raw data from the Amazon S3, passing it to the individual transcoders, and these transcoders will break down the raw data in this particular chart format, will and we will be again storing it in the Amazon S3 only. Now after processing one particular video, this Amazon S3 will communicate with the YouTube servers that hey, I've processed your raw video, and this is like the available links for each and every block of this chart. So whenever a user will request for this video, please expose these kind of URLs. So there it's like a two-way communication between the YouTube servers and the databases. Like it's always two-way communication. Okay. And the communication usually happens in a TCP protocol kind of a thing. Okay, not an UDP kind of a thing, because we need like security and stuff like that. Okay, this will be exposing the URLs of each video. And yeah, I think done. Pretty good. You can skip this part as well. Okay, I'm thinking that did I miss any of the points? The Whenever you are in doubt that hey, have you missed anything, just get onto the user flow and look whether there is any missing component or not. So creator like me will hit the post request, the AWS API gateway will now here it comes, the YouTube server. Okay, it's a distributed kind of a thing. We have scalable servers, each individually located in different locations, like one in UK, one in India, one in USA, one in Japan. So we are kind of a horizontally scaled as well as vertically scaled kind of a thing. That's a hybrid scaling. So to mention it in the interviews, instead of having a one particular single block, you will uh, kind of draw it as a cube kind of a thing. So I'll just delete this component and replace it with a cube. Cube represents scaled multiple servers. Okay. Okay, so we are pretty done over here as well. We don't have any single point of failure right now. We are processing the creator's API of uploading things. We are breaking it in chunks as well. We are processing each and every chunk as well. And then again storing it in AWS S3. Then again giving the processed videos URLs to the YouTube servers. We are storing the video metadata in the databases. I think we are done with processing the first API. Okay. Okay. Uh, now sorry. We missed out on one point. how is processing servers communicating with multiple different transcoding servers. Like, it should not happen that a task of processing one chunk is given to many different servers, and they are at their point at their endpoints processing the same thing differently, and we have like clashing kind of a thing, like whose work to take now. And for that reason, we will be having a message queue kind of a thing. We won't be doing repeated work kind of a thing. We shouldn't miss out on any of the work. So we should have a message queue, right? I think you are watching me system design problem solving videos. I think you have basic knowledge of the concepts that are involved in the system design. I'm assuming that like it's prerequisites. So let's mention the message queues. Oh, I first need to remove all these arrows now. Need to delete this. Oops. Yeah. Okay. So we need a message queue, right? Message queue. Now these message queue. So what are the different types of message queues? One is the Apache Kafka. Then Amazon also offers like a SQS kind of a thing. And we have others as well. Okay. So Amazon SQS, or well, let's say like go with the classic one, that is the Kafka. Now you'll say that we have a single message queue of Kafka, which is a single point of failure, but that's not the case. I don't want to, keep on drawing multiple Kafka queues. It's a Kafka cluster having multiple producers and having multiple consumers. Consumers in the sense we have the transporter services, and producers in the sense we are having processing servers, like multiple processing servers which are communicating constantly with the Amazon S3 database. Okay. So yeah, the transcoders will be picking up each and every task that is being present in the Apache Kafka. Okay. Okay. So we are kind of done in this particular component. We had a pretty good deep dive. I don't think we have left out. If we are left, then we'll again, backtrack. Okay. Now let's get on to the second API, that is the get video ID, which is indirectly done over here. Like for example, if the clients hit the request, like the get request of API to the gateway, it will route it to the YouTube server. It will fetch the YouTube metadata, sorry, the video metadata from the Amazon DynamoDB or Postgres, and the chunks present at the individual URLs that are being exposed by the AWS S3. Okay, but what if, like, let's get on to a worst case scenario. What if T Series releases a song and it goes viral or trending directly? So you might have observed that the YouTube in the very below the search bar, you have things like trending thing or the hot things or the kind of a viral things. Specifically, the tabs are over there. So if you get onto any of those tabs and you request to watch a video, now let's say we have 1 million users requesting for a single video. Will our YouTube servers process each of those similar requests individually? Like, will our database work 1 million times to retrieve the same data? No. Like, it's not a desirable scenario, right? So that's where, one thing as well. Let's say the Amazon S3 has the database in Mumbai, and me sitting in New York is trying to watch the same video that is being stored, in Mumbai. Okay. So my API request will travel to the database in Mumbai, get the data, retrieve the data, and then travel back to me. So that would be a hell of latency. Okay. We need to handle that as well. Also, we need to handle what if 1 million viewers are requesting to watch a single video, that is that viral kind of a thing. Now, these particular aspects are kind of are handled by CDN. CDN stands for Content Delivery Network. There are third party services like we have AWS Cloud Fleet or Akamai, or we even have, I think, Google's CDN. But the Akamai is the like the leading technology in CDN. Also, I think we have Netflix Open Connect, which kind of offers a service of CDN. Netflix, but those are specific or the proprietary to there as well. There only. So these CDN kind of a thing will what the YouTube server will do is it will communicate with the CDN like, hey, if this particular request is I have this particular request, 1 million requests, please kind of serve to them. CDN operates worldwide, so that's why I've visualized it in a cloud shape, and it will be directly communicating with the clients in the sense viewers. It will not go with through our API gateway. Okay. But we need the connection between the CDN and the AWS S3, right? Like for the first time when we are uploading any kind of a video into CDN now, we need to retrieve that data from the AWS S3. It's a bit of a trade-off now that whenever a creator like Mr. Beast or T Series is uploading any video, he won't be expecting that his video is going worldwide just another second. Like we can take few minutes and it's totally acceptable. So these kind of trade-offs you need to discuss with your interviewers. Okay. The system design interviews, we don't have a particular perfect solution. It's always that you end up having designed a different system. Okay. So we need the communication between the database and the CDN and our YouTube servers. We have already established the communication between the YouTube servers and the CDN. So now we'll join the database and the CDN. Forgive me for the worst looking arrows. Can't help. Better. Okay. So let's get on to the scenario now. Let's simulate it. 1 million users trying to watch a video uploaded by T series. Like at one point, what will happen? Clients will request to the Amazon API gateway. Spelling mistake. Okay, a gateway. It will redirect to the YouTube server. It will check, do we have it in CDN? So it should check in constant time. Like it should check the database, like the data, do we have it in the memory? Okay, so we need an in-memory database as well. What kind of data do we actually have in CDN now? So that's where we will request for a Redis kind of a database. Why Redis? It's fast, it's in memory. In memory in the sense it has a scaled RAM. It has a scaled cloud RAM. So we will check on the go whether we have that particular requested data available in our CDN. Why Redis? There are multiple options as well. I can't remember a few, but Redis is the leading in cache memory. There is memory database. In memory database is the name as is the name only of a database, but for simplicity we'll just stick to Redis cache database, which will just store the data like what all videos are preloaded into the CDN. This will kind of reduce the efforts on our YouTube servers. So 1 million users are being redirected by the AWS API gateway. The YouTube server will check, do we have preloaded that video into the CDN? No, why CDN? Because it's content delivery. We have YouTube videos, we have content. So we need content delivery network worldwide. So the CDN will, so the Redis will say, yes, you have preloaded that data. Then we'll just instruct the CDN that, hey, these are the 1 million users sitting on these locations, having these mobile numbers, mobile devices or the laptop devices or the iPod or TV devices, serve them kind of thing. And the clients will get their desired data. Now, what if an unpopular video is being requested by a user? Then the YouTube server will get the exposed URLs of the S3, get the video metadata, and then pass it to the clients. Okay, so both of the APIs are kind of served over here. And like this is the HLD now, a detailed HLD, I would say. We had deep dives on chunking transcoding. We had deep dive on CDN. We had deep dive on our databases. We had deep dive on AWS API gateway. And it's pretty done, I think. We have simulated both the APIs. We have satisfied our functional, non-functional requirements. We have done math in the sense we have done the capacity estimations and planning. And we have implemented the APIs as well. One thing that I would mention, like a bonus concept kind of a thing, how will a user kind of a thing will decide what kind of quality of data he must request. For example, initially he had high bandwidth, so he was getting a video in 1080p. But what if his bandwidth reduces? Like what if a user is sitting in a train and trying to watch a video on YouTube? His bandwidth would be variable, right? So we need to decide as a platform what kind of quality data quality we need to send it to the client. And that too we need to decide it dynamically. So this problem is solved by the software engineers. They have kind of constructed a protocol named as MPEG dash. Dash stands for dynamic adaptive streaming over HTTP. So this is kind of a thing. Also, we have HLS. HLS is also developed by Apple. So yeah, it's done. Um, so we have done with the bonus concept as well. Let me just check whether we have missed on any of the concept. We have done the capacity, watch, get, request, functional, non-functional. We have discussed databases, transcoding, MPEG dash, high level, deep dives. Yeah. So it's it's pretty done now. You can conclude your interview over here. And I think it's pretty satisfactory done as well. Just the shape of the arrows is a bit worst, a bit worse, but yeah, I think the components are pretty great over here. Yeah, done. Okay, so we are done with our system design, the YouTube system design, the HLD kind of a thing. We'll not be getting into LLD. Those are for the senior software engineers or the tech leads. So yeah, if you have any doubts, mention it in comments. I'll try hard to get back to you and solve your doubts. So yeah, signing off, Yash Bhoomkar.